This is the second video on frequency response, and here we're going to focus on plotting. The previous video then summarised what is frequency response, which is how does the behaviour of a system output change as I change the frequency of a sinusoidal input. And what we showed is you could find the amplitude of the output and the phase of the output using simple formula based upon the transfer function representation of the system. Now in general, the gain A and the phase phi depend upon the frequency, and what we want to do is explore how this change happens. So what people usually do is they use plots of the gain and phase in order to see how do these values change with frequency. Now, a core point is we want to be able to produce a quick sketch. We want to do it by hand in 10-20 seconds if possible and with minimal computation, as the ability to do this aids our insight as an engineer. It allows us to understand what's going on, and it's that insight which is needed for design. Therefore, we're going to introduce this thing called the Bode diagram, and we're going to give you some simple or fast sketching rules for getting a Bode diagram. And you'll notice what I've put at the bottom as ever, and this is really important. If you need a precise plot, use a computer. So here's some plots of frequency response. You can see here I've got the phase on the left and the gain on the right and frequency down here on the horizontal axis. What do you notice? There's lots of space in these graphs where nothing much of interest is happening. And where all the changes are happening, it's all compressed into a tiny little space on the graph. Here's a different example, and you can see the same pattern. There's lots of space on the graph where nothing of interest seems to be happening, and all the interesting stuff is compressed into a small space on the graph. And so these plots are not as useful as they could be. So while we can plot gain and phase against frequency, those plots are of limited value. In practice, we want to consider behaviours across a very wide range of frequencies, say from 0.001 radians per second up to 1000 radians seconds, and in some cases well beyond those two ranges. And we're not going to be able to do that on normal graph paper, because the low frequency parts would occupy negligible space and not be visible. So we need a plot that gives equal space to frequencies from say 0.01 to 0.1 and say 100 to 1000. So this is how we do it. We're going to use logarithmic graph paper, because what that does, it gives equal space to each frequency range. So here you can see the same space on the graph goes from 0.1 to 1, 1 to 10, 10 to 100, 100 to 1000. And that's because we've used logs on the frequency axis. However, there's still a weakness here. There's still not a lot we can see in the higher frequency range. It just looks like a flat graph. What if we try log-log graph paper? So you'll see here, I've got the same data, but different graph paper. Both of them have got logs, same logs on the horizontal axis, but the one on the left has just plotted the gain, whereas the one on the right has also used a logarithmic scale. And what's the key difference? I can now see what's happening in the high frequencies. I can actually see the pattern or the trends at high frequency. And so using log-log graph paper has turned out to be quite helpful. What is a Bode diagram then? It comprises two plots. Both plots have log 10 omega on the x-axis, which is the same as basically showing the actual values of omega, okay, but on a log scale. So you can see here that log omega, or log of 2, is 0.3. Log of 3 is 0.48. So there's two ways of displaying this information. You can either put the log value, or you can put the underlying frequency on a log scale. And it's this top one which we use because it means I can actually see what the corresponding frequency is. Okay, so what's in a Bode plot? The y-axis, we either have 20 log to the base 10 of the modulus of g of j omega. So if we're doing the gain, we actually plot the log of the gain against the log of the frequency. But if we're doing the phase, we just plot the phase itself. So here's an example of a Bode diagram. And you will get this if you just type Bode G on MATLAB. So what can you see? The gain plot is done in decibels. And you remember we said this, that decibels is 20 log to the base 10 of the modulus of G. And that's what the decibels means. Okay? The phase plot, we just plot the phase. And critically here, in degrees, not in radians. And you might find that a bit perverse, that the frequency is down here in radians per second, but we actually plot the phase in degrees. Sketching Bode diagrams. Now we know MATLAB tools can produce a precise plot fairly quickly, but we want to do sketching because it gives us insight. And that's why the rest of this video is focusing on how might you do sketching. And once you understand that, you will be able to understand the impact of compensator choices, such as where you put the poles, where you put the zeros, where you put the gain, on the Bode diagram of the compensated system. And that insight will help you when you need to do design. So, asymptotic sketching approaches. What we're going to do is characterize the asymptotes on the Bode plot. So first, what happens as frequency goes to 0? So if I take this simple factor here, 1 plus s or 1 plus j omega, you can see as omega goes to 0, the gain is 1 and the phase is 0. As omega goes to infinity, the gain is omega and the phase is 90. So I've got clear asymptotic information which I can exploit to do a very, very fast sketch. There are some errors. If you look at the corner frequency, so omega equals 1, then you'll find at that point the gain is √2. It's not 1, it's not omega, it's √2, and the phase is 45. What about a different factor? Here you see I've put the factor in the denominator, so I've got 1 over j omega plus a. So again, as omega goes to 0, you see the gain is 1 over a, and the phase is 0. As omega goes to infinity, the gain is 1 over omega, and the phase is minus 90. So again, the asymptotic information is very clear, and I can do some corrections at the corner frequency. If omega is a, the gain is 1 over a √2, and the phase is minus 45. So all these values I can understand in advance. So converting asymptotic information into the Bode diagram. So we've reminded you here, what is the Bode diagram? The gain plot and the phase plot. So let's look at this factor 1 plus j omega. What we found is that at a low frequency, the gain was essentially 1. So 20 log to the base 10 of 1 is going to give you a constant. So the Bode diagram is going to be constant at low frequencies. And you'll see here, I've emphasized that low frequencies, you've got a constant, which is, if you like, a flat line. As frequency gets large, then the gain is approximated by omega. So if I do plug this into my value here, 20 log to the base 10 of the modulus of g of j omega, I get 20 log to the base 10 of omega. And so my plot is now going to be log 10 of omega against 20 log 10 of omega. And so what you're going to get is a slope of 20 decibels per decade. Let's look at the factor 1 over a plus j omega. Well, low frequencies is going to give us something similar. We get a constant. It's a different constant, but it's still a flat line. The gain was approximated by 1 over omega. So if you basically find the decibels of that, it's minus 20 log to the base 10 of omega. And so my Bode diagram is going to reduce to a plot, horizontal axis log 10 of omega, vertical axis minus 20 log 10 of omega. In other words, a slope of minus 20 decibels per decade. So what you can see here is clear asymptotic information in terms of the slope. What about corner frequencies? Well, there are some errors at the corner frequencies. So if you put omega equals 1 into 1 plus j omega, the gain is √2. 20 log to the base 10 of √2 gives you 3 decibels. So the error at the corner frequency is 3 decibels. So that's the error compared to the steady state assumption. And similarly, if you look at the other factor we looked at, 1 over a plus j omega, again, what do you find? The error at the low frequency, at corner frequency, is 3 decibels compared to what you had at the low frequency. So we've got clear error information at the corner frequencies. 3 decibels for a numerator factor, minus 3 decibels for a denominator factor. So here's an example. You can see I've got 1 over s plus 1, or 1 over j omega plus 1, and in blue I've done my asymptote information, and in red I've done the exact Bode diagram. So what do you see? The slope goes to minus 20 decibels per decade for high frequencies. It's a constant for low frequencies. And there's a 3 decibel error. If you calculate this distance here, you'll see it's 3. So a 3 decibel error at the corner frequency. So you can do a sketch of this very, very quickly. Flat line, 20 decibels per decade slope, error of 3 at the corner. And here's the phase plot. And you see again we've got clear asymptotic information, 0 degrees at low frequency, 45 degrees or minus 45 at the corner frequency, and minus 90 at high frequencies. So general rules for asymptotes then. If we take the factor s plus a, or j omega plus a, if omega is less than a, so for small frequencies, we assume that j omega plus a is just a, and therefore we get 0 degrees for the phase and a constant for the gain. If omega is bigger than a, so large frequencies, then we assume that j omega plus a is just j omega, so we get 90 degrees for the phase and 20 decibels per decade for the gain. And at the corner frequency itself, we get some corrections. We get a root-2 correction to the gain and a 45-degree correction to the phase. And what we're going to do is use these general rules, and the key thing is for each factor in turn. So these rules apply to a single factor, and if we apply it to each factor in turn, we can quickly build up an overall gain and phase estimate. And we'll show you how to do this. So you can get a good idea of what a Bode plot will look like for a single factor by sketching asymptotes for large and small omega, and basically making a correction at the corner frequency and joining your observations by a smooth curve. Next, we want to see how do we extend this when we have multiple simple factors. And you'll note I'm not going to do quadratic factors here. So here's what you need to know. The key rule is this, the additive properties of Bode plots. If you imagine you had g equals g1 times g2, then the phase of g is the phase of g1 plus the phase of g2. And here's the key thing. The Bode plot took logs of the gain, and the log of the modulus of g1 times g2 is the log of the modulus of g1 plus the log of the modulus of g2. So in decibels, you just add the gains. And here's the key thing. If you multiply factors, you get addition in both Bode plots. And it's this property that we're going to exploit to allow us to do very fast sketching. So I'm going to do this example more slowly, and then we're going to get much, much faster. So we're going to do the asymptotic approximations for each factor in turn. So let's start with this factor j omega plus 1. If omega is less than 1, I'm going to assume it's 1. If omega is 1, you can put, we're going to get root 2. And sorry, I won't put root 2 for now. I'll just put 1 for now, and we'll worry about the correction later. And if omega is bigger than 1, we're going to have omega as our approximation, or I put j omega to represent that it's a complex number. What about the j omega plus 5? If omega is less than 1, we put 5. If omega is 1, we put 5. If omega is from 1 and 5, we put 5. 5, we put 5. And then if omega is greater than 5, we put j omega. So I'm just putting my asymptotic approximations, ignoring the corner frequencies for now. So what do I get for my overall g of j omega? So I'm going to get 1 over 5, 1 over 5, 1 over 5 j omega, 1 over 5 j omega, and then 1 over j omega squared. So you can see how quick that is just using this table. And now I want to start asking myself, what have I got in my Bode diagram? So here I've got 20 log to the base 10 of 1 over 5 and a phase of 0. At the corner frequency, I'm going to use the same thing for now, but notice you're going to have your 3 dB correction. And the phase, you're going to have a 45 degree correction because of the s plus 1. What about between omega between 1 and 5? You're now going to get a minus 20 decibels per decade slope, because you can see I've got this omega in the denominator, and the phase you're going to assume is minus 90. Okay, because you've now got this j, hopefully you can see that, I've got this j in the denominator, so that gives me minus 90. At omega equals 5, I'm going to do the same thing. I'm not going to worry about that particular line there. And I'm going to put, I have minus 90, and then I'll get my 45 degree correction. And then at omega greater than 5, I'm going to end up with minus 40 decibels per decade, because you can see I've now got an omega squared. And I'm going to end up with a minus 180 because I've got a j squared. So I've done that in the table just so you can see roughly what's happening. But now we're going to go straight to the graph, and we're going to do it more quickly. So here's the graph. And you can see at low frequencies, we have a constant, all right, all the way up to here, where omega equals 1. Then after omega, oh, so we're doing the phase first, all right, so phase, we get minus 180 degrees at high frequencies, 90 degrees at the geometric mean of the two, and you'll see, roughly speaking, I say roughly, there are 45 degree corrections. It's not exact, because this is an approximation, okay? If you look at the gain plot, you see you've got, roughly speaking, 3 decibel corrections at the corner frequencies, a slope of minus 20 decibels per decade between the two frequencies, and minus 40 decibels per decade at high frequencies. So you can see the asymptotic plots in blue lines are actually quite close to the real plot. Now, we're going to show some examples here where we're going to get quicker and quicker to show how you can actually do this as a sketch, because once you can do this quickly, you'll see the benefit. So here's my example with no information at all. I've got 10 s plus 0.4 over s plus 1, s plus 5. So where are my corner frequencies first? So I've got a corner frequency here at 0.4, a corner frequency here at 1, and a corner frequency here at 5. So mark your corner frequencies so we know what we're talking about. And you'll see I've given you the low frequency gain over here. It's minus 2 decibels. So basically up to 0.4, we're going to have a flat line of minus 2 decibels. And then what's going to happen is we're going to hit this 0. Because it's a 0, we're now going to approximate that factor by omega, and so we're going to get a slope going up of 20 decibels per decade. So I've gone through a 0, so my slope goes to 20 decibels per decade. I then meet a pole, so the slope changes by minus 20 decibels per decade, so it now goes flat. And then I meet another pole, and so the slope becomes here minus 20 decibels per decade. So hopefully you can see how quickly you could do that sketch. I start with my low frequency gain, and then I just change the slope by 20 as I go through a 0 or pole, plus 20 if I go through a 0, minus 20 if I go through a pole. Now I can do a similar thing with the phase. So for low frequencies, the phase is 0. I go through a 0, so the phase is going to go up to 90. This is the asymptote. I go through the pole, comes down by 90. I go through another pole, comes down by 90. So those are the asymptotic information. And now what I need to do is make a few corrections. Now I'm not going to do it here because I don't want to waste your time, but basically what you're going to have to do is calculate the argument of, say, g of j1 and put that value in. See what I've done with that cross there. You'll probably need a couple of values in order to pin your plot, and then your plot's going to, the asymptotes give you useful information, and your plot's going to do something like that. Now remember, this is a sketch. We're not trying to be exact. Okay, we want to do this very quickly. If you want it to be exact, turn on MATLAB. So here's another example, and I'm basically going to do this example very, very quickly. So the low frequency gain is 6 decibels, and I need to put in my poles and zeros. So I've got 1 at 1, I've got 1 at 2, and I've got 1 at 10. And if I put in a frequency of 1, you can see that the modulus of G is approximately 2, which is 6 decibels. So I can pin my asymptote at that value there, which is 6. For low frequencies, I've got a minus 20 decibels per decade, and I can see that because of this integrator, this 1 over S. I then go through a pole at 1, so the slope goes down to minus 40. I then go through a 0, so the slope goes up to minus 20, and another pole, so it goes to minus 40. So the slopes, minus 40, minus 20, minus 40. Now you'll see this is a very, very rough sketch because I'm just trying to get an impression of what is going on. I'm not trying to be too accurate. Similarly, if I do the phase, we start at minus 90 because of the integrator. I then go through a pole, so it goes down to minus 180. I then go through a 0, so it comes up again. Go along, come to another pole, goes down again. Now don't worry about the fact that these asymptotes aren't overly precise. Add an exact calculation. It's going to be something like that. And then you'll see that probably your phase is going to do something like this. Okay? The key thing is I'm just trying to get an impression at this point. I'm not trying to be overly precise. So how am I going to use these asymptotes for design? That's the most important thing coming next. So let's look at a lead compensator, and I'll skip on this. The main thing is you see the structure, but that structure will be clear on this graph. So here's an example of a lead compensator. It's got some gain K, it's got a 0 and a pole, and you'll see the 0 is smaller than the pole. So we've got the 0 with a corner frequency of 0.2 and the pole with a corner frequency of 1. And the key thing is you can see I've got this slope of plus 20 decibels per decade between the 0 and the pole. And what does this tell you? It tells you that the gain is bigger at high frequency than it is at low frequency. What about the phase? Well, again, because the 0 is smaller, and then you look at the way these asymptotes here have gone up to plus 90, what you can see is the phase is positive. And it won't surprise you that the phase peak is at the geometric mean of the two corner frequencies. So in other words, it's the square root of 0.2. So what I can see is that I've got positive phase. So just using these asymptote information, these blue lines, I can deduce approximately where the actual red lines will be, and I can see what's going on, and I can see how it relates to the corner frequencies that I choose. I can do the same for a lag compensator. So here's a lag compensator, and here you'll see the difference is that the 0 is now big and the pole is small. So I've got a 0 at 1, a pole at 1 and a 0 at 5. And so what happens now is I end up with a slope minus 20 between the pole and the 0. So it means that the gain is lower at high frequency than at low frequency. And I can see that shape very clearly just by sketching these asymptotes. I don't need to bother about the red line. The asymptotes are good enough. And similarly with the phase, I can see this negative phase very, very clearly just using the asymptote information. I don't really need to know exactly where that red line is. Now, why is that important? If we want to do design and we're going to add a lead or a lag compensator, what we're going to do is use the property that multiplying factors leads to addition in both Bode plots. So here's the example I'm going to use. I've got my system G here, and I've got my compensator M here. All right, and what I'm going to do is plot the Bode diagram for G, and you can use asymptotes if you like. Plot the Bode diagram for M, and again you can use asymptotes if you like. And then finally, I'm just going to add those two plots together. So here I'm going to show you what's happened. G is the blue curve. So here's the blue curve you get. And you could get a very similar curve just from the asymptotes if you wanted, if you were doing it on the back of an envelope. And here is the sort of, if you like, I can put some asymptotes in here just if you wanted. The asymptotes would do something like this if you wanted them, and the asymptotes for this one would do something like this. So you can see roughly what the compensator is doing. Now, how do I get the Bode diagram for my compensated system, that is G times M? Well, I look at the phase plot, and I can see there's a phase drop at omega equals √6, and I can see how big that phase drop is. And the same phase drop will occur here. So you can see I can get the new value for GM just by applying the same phase drop compared to G. Similarly for the gain, I can see there's a gain uplift at a low frequency. So I can apply the same gain uplift here at a given frequency. So very simply, I can do some sketches, and you'll see the corner frequencies roughly here and here. I can see where the corner frequencies, so I can basically deduce this information, gain some insight without having to do precise plots. So some summary. We've introduced the Bode diagram for plotting frequency response information and shown that you can form rapid sketches of these diagrams using asymptotic information. And the insight gained from sketching is invaluable for design because without a precise plot, you can still see roughly where you want your pole zero to be in your compensator and what magnitudes you need. Obviously, if you want precise plots, you're going to go to Bode, but the point is there's no point going to Bode until you know what you're doing, until you understand what you're doing, and that's what sketches will do for you.